Star composition secret. What are the stars made of? It's a question humanity has asked since the first person looked up into the velvet black of the night sky. For millennia, the answer was pure speculation. Divine fire, celestial jewels, holes in the firmament. But by the dawn of the 20th century, science believed it had a concrete, sensible answer. The consensus held by the most brilliant minds of the age was that the stars, including our own sun, were fundamentally made of the same stuff as the Earth. They were cosmic cousins, compositionally identical. The sun was simply a much, much hotter version of our own planet. A great glowing ball of iron, silicon, oxygen, and all the other heavy elements we find beneath our feet. This was the bedrock truth of astronomy, a comfortable, logical idea that placed us in a familiar-looking universe. It made sense. It was elegant. And in 1925, a quiet, determined 25-year-old woman named Cecilia Payne was about to prove that it was completely, utterly, and spectacularly wrong. Her discovery wouldn't just be a minor correction. It would be a scientific earthquake, a fundamental rewriting of our place in the cosmos. To understand the sheer audacity of her work, you have to understand Cecilia Payne herself. Born in England in 1900, she was a force of intellectual nature from the very beginning. She won a scholarship to Cambridge University to study botany, physics, and chemistry, but her path was irrevocably altered after attending a lecture by the great Arthur Eddington. He was speaking about his 1919 expedition to observe a solar eclipse, which provided the first stunning proof of Einstein's theory of general relativity. For Payne, it was a moment of pure epiphany. The world of plants and earthbound chemistry suddenly seemed small. The universe was calling. She switched her focus to astronomy, but quickly ran into a wall of institutional sexism. Cambridge at the time refused to grant degrees to women no matter how brilliant they were. Her path to a real career in the field she loved was blocked. So she looked across the Atlantic. She sought out and won a fellowship to the Harvard College Observatory in the United States, a place that, while far from a paradise of equality, had a unique reputation. It was home to a group of women known as the Harvard Computers. These were remarkable individuals, hired by the observatory's director to perform the painstaking work of analyzing the vast collection of photographic glass plates that captured the light from hundreds of thousands of stars. It was tedious, meticulous work, and it was considered women's work at the time, less prestigious and certainly less paid than the theoretical work done by the male astronomers. But within this mountain of data lay the secrets of the universe, waiting for someone with the right key to unlock them. That key was a technique called spectroscopy. When you pass starlight through a prism, it doesn't just create a pretty rainbow. It creates a rainbow crossed by thousands of tiny dark lines. These are absorption lines, and each line is a chemical fingerprint, a unique signature left by a specific element in the star's atmosphere absorbing certain wavelengths of light. For decades, astronomers had been using these lines to identify the elements in stars. They saw the fingerprints of calcium, iron, and sodium, all elements common on Earth. The logic seemed simple. The darker and thicker the line, the more of that element there must be. And based on this method, the conclusion was inescapable. The sun and the Earth were cosmic twins. But Cecilia Payne wasn't just there to catalog. She was there to understand. She was armed with a revolutionary new tool that most of the old guard of astronomy had yet to fully grasp: the burgeoning field of quantum physics. Specifically, she utilized the work of Indian physicist Meghnad Saha and his groundbreaking ionization equation. Saha's work showed that the temperature of a star dramatically affects how its atoms behave. At extreme temperatures, atoms lose their electrons. They become ionized. An ionized atom leaves a completely different spectral fingerprint than a neutral one. This was the missing piece of the puzzle. The old guard had been reading the fingerprints all wrong. They were assuming that the strength of a spectral line was a simple measure of abundance. Payne realized it was a complex dance between abundance, temperature, and pressure. It was like trying to judge the size of a crowd by how loudly they were shouting without realizing some people were shouting in a soundproof room. With this new theoretical framework, Payne began what can only be described as a heroic effort of analysis. For her doctoral thesis, she meticulously examined the spectra of hundreds of stars, applying Saha's equations to correct for the temperature effects. She was unraveling the data in a way no one had before. And as she crunched the numbers, a truly shocking picture began to emerge. The lines for elements like iron and silicon were prominent not because they were abundant, but because at stellar temperatures, they were incredibly efficient at absorbing light. The elements that seemed almost invisible, whose spectral lines were faint and unassuming, were the ones that were truly dominant. Those elements were hydrogen and helium. Her calculations showed that hydrogen was not just another minor ingredient in the cosmic recipe, it was the main course. It was 1,000,000 times more abundant than the heavy elements everyone thought were dominant. Helium was the second most abundant by a huge margin. Her conclusion was as profound as it was radical. The universe was not made of the same stuff as us. We, on our rocky little planet, were the cosmic exception, not the rule. The stars were something else entirely. They were vast, magnificent balls of the two simplest, lightest elements in existence. In 1925, she compiled this earth-shattering work into her PhD thesis titled Stellar Atmospheres. It was a masterpiece of scientific reasoning and empirical evidence. Decades later, other astronomers would look back on it and declare it, without hyperbole, undoubtedly the most brilliant PhD thesis ever written in astronomy. She had solved one of the oldest mysteries in science. She had discovered the truth. But now she had to convince the world, and the world was not ready to listen. Forced retraction scandal. Cecilia Payne had just handed in a work of pure genius. She had single-handedly discovered the fundamental composition of the universe. In a just world, the publication of her thesis, Stellar Atmospheres, would have been met with immediate acclaim, prestigious awards, and a fast track to a professorship. Her name should have been etched into the annals of science overnight. But the world of 1920s academia was not that world, especially not for a woman. Instead of celebration, Payne's revolutionary conclusion was met with a wall of entrenched dogma and condescending disbelief. The scientific establishment, a rigid hierarchy dominated by older men, looked at her findings not with wonder, but with suspicion. Her results were too radical, too disruptive. They flew in the face of decades of accepted wisdom. And one man, more than any other, stood as the great gatekeeper of that wisdom. His name was Henry Norris Russell. If 20th century American astronomy had a final boss, it was Henry Norris Russell. He was the director of the Princeton University Observatory, a towering figure of immense influence and prestige. His theories on stellar evolution and composition were considered gospel. He was the expert, the authority whose opinion could make or break a career. And it was Russell who was chosen to review Payne's doctoral thesis. He read her meticulous calculations, her careful application of quantum theory, and her stunning conclusion that stars were almost entirely hydrogen and helium. And he simply could not accept it. It contradicted his own work and the prevailing model he had helped build. To him, the sheer abundance of hydrogen she was proposing was, in his own words, clearly impossible. The disparity with the Earth's composition was just too vast to be believable. It had to be a mistake, an error in her calculations, a youthful overreach from a student who didn't know any better. This wasn't a simple academic disagreement between equals. This was a titan of the field delivering a verdict to a 25-year-old woman who, despite her brilliance, held no official position, no power, and no security. She was a foreign national on a temporary fellowship. Her entire future in her chosen field depended on the approval of men like Russell. He didn't just disagree with her. He actively pressured her to remove the most important conclusion from her work. Imagine the situation. You have dedicated years of your life to a single problem. You have worked tirelessly, applying cutting-edge physics to a mountain of data. You have made a discovery that you know in your bones is correct. It is the single greatest achievement of your life. And then the most powerful man in your profession tells you to your face that you are wrong, that your discovery is an illusion, and that you must disavow it if you want your work to be accepted. The pressure must have been immense, the choice agonizing. To stand her ground would be professional suicide. She would be branded a crank, her thesis rejected, and her career likely over before it had even begun. To acquiesce would be to betray her own science, to willingly sabotage her own monumental discovery. In the end, she made a heartbreaking compromise. In order to get her PhD and have her thesis published, Cecilia Payne added a single, devastating sentence to her work. Regarding her own finding that hydrogen was the overwhelmingly dominant element in the cosmos, she wrote that the calculated abundance was almost certainly not real. It was an act of intellectual self-immolation, forced upon her by the weight of authority. She had discovered the secret of the stars and was then coerced into calling her own discovery a lie. A single sentence that kneecapped her own magnum opus. With that sentence, the scientific revolution she had started was stopped dead in its tracks. The thesis was published. She was awarded her doctorate, the first ever from Radcliffe College in astronomy. But her central, universe-altering truth was officially dismissed as a spurious artifact. This incident wasn't just a personal tragedy for Payne. It was a stark symptom of a deeply diseased system. The 1920s were a time of immense systemic bias against women in science. They were often denied access to the best universities, barred from using primary research equipment like major telescopes, and systematically paid far less than their male counterparts for the same work. Even at Harvard, after receiving her doctorate, Payne was not given the title of astronomer. For years, she was officially a technical assistant to the director, Harlow Shapley, despite conducting her own world-class research. Her salary was pitifully low, classified alongside the observatory secretarial staff. She had to fight for every scrap of recognition, for every opportunity to lecture, for every student she wanted to advise. The forced retraction was not an isolated event, but the most egregious example of the patriarchal barriers that constantly sought to diminish her contributions and silence her voice. It was a clear message from the establishment. We will take your data, we will use your labor, but we will not accept your genius if it dares to challenge our own. The truth had been spoken, but a powerful man had silenced it, leaving the world of astronomy to continue believing a comfortable lie for years to come.
Truth revealed, legacy science, for all its human flaws, has a wonderful, stubborn bias towards the truth. You can ignore it, you can dismiss it, you can force it into the footnotes, but you can't make it go away. The data doesn't lie. And Cecilia Payne's data, showing a universe awash in hydrogen, continued to haunt the man who had dismissed it. Henry Norris Russell, despite having publicly rejected her conclusion as impossible, was too good a scientist to simply forget about it. The discrepancy gnawed at him. He knew Payne's work was meticulous, even if he couldn't accept its final implication. So he decided to investigate the problem himself. Over the next 4 years, using his own methods and approaching the problem from a different theoretical angle, he began to analyze the composition of the sun. He gathered new data, refined his calculations, and slowly, painstakingly, began to work towards an answer. And in 1929, 4 years after he had forced a young woman to retract her life's work, Henry Norris Russell arrived at a startling conclusion. Cecilia Payne had been right all along. The sun was, in fact, composed almost entirely of hydrogen. It was a moment of immense historical irony. The very man who had declared the truth impossible had now independently verified it. He prepared to publish his findings, knowing they would be hailed as a major breakthrough. But what would he say about the original discovery? How would he acknowledge the work of the woman he had silenced? In his 1929 paper, Russell did, to his credit, mention her. He wrote that the high abundance of hydrogen and helium in stellar atmospheres was a conclusion first advanced by C.H. Payne. On the surface, it seems like a fair acknowledgement. But in the politics of scientific credit, it was a masterful understatement that served to obscure the real story. It was a passing nod, a tip of the cap, not the full-throated admission of her priority and his own error that justice demanded. It failed to mention that her conclusion was not just advanced, but was the central, quantitative result of her entire thesis, or that he himself had been the one to suppress it. The impact was immediate and decisive. Russell was the established giant. Payne was the relatively unknown junior researcher. The scientific community, by and large, gave him the credit. His paper became the landmark, her thesis a footnote. For decades, textbooks and university courses would teach that Henry Norris Russell discovered the composition of the stars. The stolen truth had been laundered and presented to the world, with the original discoverer relegated to a supporting role in her own story. But Cecilia Payne was not the kind of person to be defined by injustice. While the world was slowly catching up to the truth she had uncovered in 1925, she was already moving on to new astronomical frontiers. She embarked on a long, prolific, and utterly brilliant career at the Harvard College Observatory. Her scientific output was staggering. She, along with her husband, the Russian astronomer Sergei Gaposchkin, conducted a monumental study of variable stars, stars whose brightness changes over time. They and their students made over 3 million observations of these stars, primarily in the Magellanic Clouds, providing a foundational data set that would be crucial for understanding stellar evolution and measuring cosmic distances. She published several books, including Stars of High Luminosity and Variable Stars, which became standard texts in the field. She was a dedicated and inspiring teacher, mentoring a new generation of astronomers. Slowly, painstakingly, she broke through the barriers that had been placed in her way. For 28 years after receiving her doctorate, Harvard refused to give her a proper professorial title. It wasn't until 1956, after the previous observatory director had retired, that she was finally made a full professor, the first woman in Harvard's history to achieve the rank. Shortly after, she was appointed chair of the Department of Astronomy, another first for a woman at Harvard. She had outlasted her detractors and, through sheer, undeniable brilliance and perseverance, forced the establishment to recognize her. And as time went on, the true story of her 1925 discovery began to be re-examined. Historians of science and fellow astronomers looked back at her original thesis and Russell's subsequent paper and saw the injustice for what it was. Today, there is no debate. Cecilia Payne-Gaposchkin is recognized as the person who discovered the composition of the universe. Her thesis is rightly hailed as the founding document of modern stellar astrophysics. Everything we know about how stars are born, how they live, how they forge new elements in their cores, and how they die, rests on the foundation she laid. Her story is a powerful lesson that a great mind can be dismissed, a brilliant discovery can be suppressed, but the truth, like a star, will eventually have its light shine through. Her genius, once silenced, now illuminates the cosmos.